It's been a long fall break. Lots of good stuff to talk about. All right, so we're going to have homework due today. So hope you guys are not there. And then we will have continued assignments coming. So. All right. So what we're talking about right now is wave mechanics. Wave mechanics is really what we're looking at is quantum mechanics in the position or momentum representations. And the physical context we're looking at is thinking about a particle of some mass and moving a single particle at the moment, moving under the influence of some conservative potential. And the Hamiltonian then is a familiar form for mechanics, kinetic and potential energy. And the Schrödinger equation then takes the form of wave equations. So the time-dependent Schrödinger equation, as we've derived it, takes the form of a time-dependent wave equation. And the time-independent Schrödinger equation, which tells us about the stationary states, i.e. the energy eigenstates of the system, takes the form of a time-independent wave equation. Of this form. And if we think about, as we discussed, the case where the particle is a free particle, where there's no force, no external potential, then the Hamiltonian is just kinetic energy. The time-independent Schrödinger equation takes this form, which is a familiar wave equation. It's the Helmholtz equation. Okay. And we can instantly write down the eigenstates of the Hamiltonian, the stationary states, because we see that this Hamiltonian clearly commutes with all components of momentum. And thus, the momentum eigenstates, the eigenstates of the momentum operator, are also eigenstates of the Hamiltonian. So that's a way we can write down instantly the free particle stationary states. So they are eigenstates of the Hamiltonian with this eigenvalue. Okay? And the form of those, the wave function, is of course the position representation of the momentum eigenvectors are plane waves. Right? So from this we see that if we have a free particle, we can talk about free particle eigenstates as plane waves with definite momentum. And those plane waves, of course, we remember from our study of waves, have this form where this parameter is the wave vector. And thus we relate from this the de Broglie relationship, which relates the momentum to the wavelength, or the momentum to the wave vector, the momentum vector to the wave vector. And the relationship between the wavelength of the particle and the wave number is here, and that's the de Broglie relationship. Right? Okay. And from this, we see for a free particle, we derive the dispersion relation that tells us the relationship between the frequency and wavelength, or frequency and wave number. And that is really, so the wave particle duality expression tells us that the energy relationship between energy and momentum translates in the wave language into a relationship between the frequency and the wave number, or the frequency and the wave number. Okay? And for a free particle, we have this kind of quadratic relationship, okay? Which tells us that a free particle, or a non-relativistic particle of mass m, has a quadratic dispersion relation, which means that the waves disperse. Different wavelengths move at different phase velocities. And because of that, if you have a wave packet, which has some spread in momentum, it will disperse. Okay? And you're finishing up your homework on that problem, if you haven't already done that. Okay? Any questions? All right. So, I want to continue here today to get a deeper intuition and understanding of the nature of the wave function and the relationship of wave mechanics, quantum mechanics, and classical mechanics. Okay, so let me begin. So we have, of course, seen the most fundamental thing, the way we think about the wave function. Of course, if we have a wave function, in this case, for a particle moving in 3D, and I look at the square of the wave function, well, this we have interpreted as the probability density. That is to say, if I look at some small volume, that this is the probability to find the particle in a projective measurement in the region within this volume. Of course, we can think about this if we like. This is the representation of the state in the position representation. Or more generally, if I have a density operator, meaning I have a mixed state, what is the probability density to find the particle at position x? If I had a, right, so we know from our studies that to find the probability, it's the diagonal matrix elements of the density operator tell us the probability to be in that state. In this case, it's the probability density, right? We can also, though, talk about the off-diagonal elements in the position representation, right? We could. How would you interpret that?
Coherences.
They're the coherences. And what do the coherences mean?
Interference between the states.
It's something about interference. It's the possibility of seeing interference between these two positions in space. That is to say, if I sent the wave from through two slits, one at x and one at x prime, I would want to know whether there was coherence between those 2 points and whether I would see on a screen interference. Okay, so the off-diagonal elements tell me. I mean, if this were a pure state, well, this is for a pure state. This, which is the product of psi at x prime and psi star at a different x. Okay. So this is telling me about the coherences. And if I have generally a mixed state, it could be the case that the coherence length, the distance over which the wave function exhibits coherence, need not be the same thing as the uncertainty in the position. Okay, I can have a situation where I have, you know, a beam that has a big uncertainty where the particle is, but it may not exhibit coherence over that way. Okay, so that's one part of the interpretation, the probability density and the coherences. Let's take a look though. So let me call this probability density here, just from this point, I'll call it rho of x and t. That's the diagonal matrix element. Okay. Okay, let's look at this. It doesn't really matter whether it's a pure or mixed state. It's easiest to deal with this for a pure state. We would just have to average over the ensemble of possible pure states if we had a general mixed state. So I'll just focus my attention for the remainder on the pure state case. And let's consider how the probability density changes as a function of time. Okay? So that's equal to that, right? For a pure state, and I'm going to say, if we had a mixed state, we would just average over the ensemble of states, so it doesn't change anything. And now we know how these guys evolve according to the time-dependent Schrodinger equation. Okay? So this is equal to minus I over h bar, h psi star, plus psi star minus I over h bar, the Hamiltonian on psi, all in the position representation. Now, this will be equal to what? Well, the term that has to do with the potential will cancel, right? Because the star of this gives me a plus I, and here I got a minus I, and the potential term will cancel out. So all I'm left with here then is minus I over h bar plus times minus h bar squared over 2m Laplacian star psi minus I over h bar psi star h bar squared minus h bar squared over 2m Laplacian psi. Okay, determine the potential, cancel out. All right. So now, right. Okay. So now I'm going to use the following vector calculus identity that the gradient, the divergence of the vector field that is some vector times a scalar is the scalar times the gradient, the divergence of the vector plus the A dotted into vector calc identities that quickly derive with a couple of epsilon k's or something like that. In this case, it's just some minors. So using that, the following holds. Let me get this at the top where you can see it. A new vector j of x, where j is equal to 1/2 psi star, the momentum operator, psi plus bless you. This representation. Okay? So that's just a matter of, you know, playing around a little bit with vector calculus. So, you recognize this equation?
The continuity equation?
It's the continuity equation, thank you. This is the continuity equation, familiar from fluid dynamics, but probably more familiar to you from electricity magnetism, where J is the current of charge and rho is the charge density. Okay? So this equation represents a kind of, the continuity equation is a picture in which I think about some kind of fluid flow. And what the continuity equation tells me is that the total amount of fluid is conserved. The total amount of the stuff that makes up the fluid is conserved. And what it says, if I look at this, if I integrate this over some region, a volume of space, so if I look at the integral of this over some volume, okay. So now this is this. Well, that by the divergence theorem is the flow of the fluid, or the current, the flux of the current out of the surface with a minus sign. Which is to say, if the stuff inside the volume is decreasing, the only way that can happen is if it's leaving. Stuff is neither created nor destroyed, it just moves around. That's what the continuity equation tells us. It tells us that the stuff is neither created nor destroyed, it just moves from one place to another. That's what the continuity equation tells us. So how do we then interpret that in the context of what we're talking about here? Rho here is what? It's the density of what? Not the density of charge necessarily. Or what is it? What is it? It's the probability density. Right? And the J here is defined as the probability current. That is to say, this is, in some sense, the continuity equation in this context is saying something about the conservation of probability. probability to find a particle somewhere. This is saying that the particle is neither created nor destroyed. It just moves around. And there's a flux of probability if the particle is moving. So let's say the probability density can change with time because the particle can move. Okay? Now, of course, we know in relativistic quantum mechanics, particles are created and destroyed. So we have to think harder about that problem, what we're talking about when we have sort of the equivalent of the continuity equation in quantum field theory. Maybe we'll get to that at some point. But for the moment, in non-relativistic theory, the particle is neither created nor destroyed. Okay? And you notice that this came from the fact in the mathematics that the potential was real. If the potential had an imaginary part in it, there was somehow a complex potential, then it wouldn't have canceled, right, in this equation. So we got from here to here because V is real. So one way to mock up absorption of a particle is to put an imaginary part in the potential. Kind of like you put an imaginary part in the index of refraction when you want to deal with absorption. Okay? Come to that a little bit later. All right. So probability current and conservation. All right. So to further get some insight into the nature of wave mechanics, we're going to make a connection to geometric optics through what's known as the iconoform. Okay. So, what's the iconoform? So I'm going to express the wave function it's a complex number. It has an amplitude and a phase, right? A magnitude and a phase. So I'm going to write it as a real amplitude and a phase. Now that phase I'm going to write in units of h bar for reasons that will become apparent later. You don't have to do that, but I'm just going to write it so that it has the units of amplitude. So this is the amplitude and the phase. They're both real functions, right? All right, that's just an ansatz. It's an assumed form. We've done no approximation. We're just going to plug it in. So let's plug this into before I do that, we could say just a couple of things quickly. Firstly, note that the probability density is just the square of the amplitude. And moreover, what we would say is that the surfaces of constant S are wavefronts in wave theory. All right, now let's plug this in time-dependent Schrödinger equation. Now it's a bit of a drag to do that because we have to take the Laplacian of this thing, right? And then we have to use, the product rule on that. And then we have all kinds of vector identities to deal with. But so I'm not going to do all that. I'm just going to write down the answer. And that's why I'm cheating with my iPad today. I'm too lazy. Do that algebra on the board right now. All right, so look, we could see what's going on here, right? I mean, the right-hand side, you take the derivative with respect to time, that's the, what was the left-hand side of the equation over there? You got a derivative of the amplitude and a derivative of the phase, and the derivative, and then, you got the e to the I thing, and I cancel that on both sides. Over here, I have the Laplacian, and that has all these different derivatives. You have second derivatives on the amplitude, you have second derivatives on the phase, and then all the cross terms, where you take, a derivative of each way. So that's where it's going on. You just kind of do it all. Okay? All right, so that doesn't look helpful. However, it is. So everything here, as I said, A and S are real functions, which means that separately, the real part of this equation equals the real part of this equation, or this side, and the imaginary part equals the imaginary part. So we have two equations, one for the real part of this equation, and one for the imaginary part of this equation. All right? So separating real and imaginary parts. We have the following. So that still doesn't quite look useful or intuitive. Doesn't seem like there's a lot yet to be gleaned from that, but there is. And so what I'm going to do in this equation is I'm going to multiply both sides by A, and then divide by 2. And here's what I do.
Shouldn't it be over H bar?
Possibly. You can put in all the H bars afterwards. I'm not going to wear that the H bars. So, what we have is the following. That's the real equation. And the other equation is the following. These two equations. All right, so now we're getting somewhere. What can we say about these two equations? Well, let's look at this first equation up here. Anyone have any thoughts about that equation?
That it's exactly kind of a scalar.
It's got it, it's got that. But what does it look like?
Continuity.
Looks like the continuity equation, right? In fact, it is the continuity equation, because what is a squared?
Probability.
A squared is rho. It's probability density. So this is equivalent to, this is d by dt of rho is minus, right, the continuity equation. Equation that says that the particle isn't lost or created. But what is J then? What is the probability current when expressed in the atomic form?
It's like a
Sorry, there's a in here. It's not multiplying today. Yep, that's right. So look at it. It's equal to rho times this. The gradient of the phase divided by the mass. Now, if I have a fluid, and the fluid, let's go back to the needle here. Let's go back to our picture of the fluid. And let's say that right here at this position, the fluid is flowing with some velocity at that position. Okay? And suppose the local density right at that position is rho. I ask you, what is the local current density at that position? If I have fluid flowing, those of you who know fluid dynamics should know this stuff. Rho times V. Okay. So, what this tells me is the following. That the local probability is flowing with a local velocity. This is the effective local velocity. At that position. And what is that? It's saying that the mass times the local, this is the effective local momentum at that position of the flow. So, how do we interpret that picture? Well, what is S? Well, S was the phase. And we said that contours or surfaces of constant S, so this is a locus of points, a surface where S of x and t is a constant. What is the gradient then? The gradient are the normals to this. So the local gradient of the wavefronts represent the way in which the probability is flowing. And these, in optics, are known as the rays. So if I have a a wavefront and I want to know what direction the light ray is moving, the light ray is moving perpendicular to the wavefront. It's the local ray. Okay, well, moreover, if we look at, now let's look at this equation, which tells us how those wavefronts change with time. If we look at this equation, I'll call this the limit where h bar goes to 0. Let's consider that first. Let's suppose h bar was 0. Then what is this equation? That equation is this. If I which is saying the Hamiltonian evaluated at x and p is the gradient of s plus ds dt is 0. This equation actually has a name in classical mechanics. You probably haven't studied it, and you probably never will because you never take 503. She said anymore. But it's an important equation in classical mechanics, and it has a name. It's called the Hamilton-Jacobi equation. What is the Hamilton-Jacobi equation? Well, the Hamilton-Jacobi equation is another way of solving for the classical trajectories of a particle of mass m in this case, moving under the influence of this potential. If you solve this equation, and what it tells me is that if I find s, then p, and solve this equation, then whatever I get for s from this equation, the local momentum at that position in time is the gradient. This function is known as Hamilton's principal function. So, what is the takeaway message from here? Well, what it's saying that in some sense, and then we'll have to make this much more precise, in this limit that h bar goes to 0, I don't have to explain what the heck we mean by that in a moment, that quantum mechanics, in some way, has as its limit classical dynamics. That is to say that the particle moves with a momentum that's given exactly from what you would get from classical mechanics for that Hamiltonian. It moves along a trajectory that can always be solved from the Hamilton-Jacobi equation as the local rays to wavefronts. Hamilton knew that well before quantum mechanics. Well, not some decades. I forget when the hell Hamilton was, but it's hard to know. Quantum mechanics. I know, sometime in the 19th century. Now, what is that limit here? What we really did is that we ignored a term here. So let's go back to that. I'll come back to this. So there's this term here. The term that has h bar in it. And that's the term that we neglected. Okay? So the Hamilton-Jacobi equation is a good approximation. For example, when this is much, much bigger than this. Well, let's get a feeling for what that might mean. Let's suppose I had something that was kind of like a plane wave. With some amplitude e to the I equal to R. Something that looks like that. So this approximation then is saying that h bar squared over 2n is much, much bigger than h bar squared over 2n. Right? Or just getting rid of all that, that k is much, much bigger than the square root of that. Now, let's say that there's some characteristic length scale over which the wave function changes its amplitude. Let me go above here. So I'm just going to say this thing is on the order of there's some length scale which changes. This is just a very rough kind of picture. Then this equation here is basically saying that k is much, much bigger than 1 over that length scale. Which is to say that the wavelength over 2 pi, forget about the 2 pi because all this is very rough, is tiny compared to this one. Yeah?
Can you describe the length again?
So the length scale is saying something about the scale over which this amplitude is changing. So in some sense what that length scale is telling us that amplitude is changing because it's not really a free particle, there's a potential. So really, and it's an important point here, that this length scale is sort of the scale over which V changes. So it's saying something about the particle is moving in this potential. Potential is not uniform, otherwise it would be no, right? And how does the particle move in this potential? Well, if the wavelength associated with that momentum is tiny compared to that scale, then the wave nature of the problem is negligible. And it looks more like trajectories of rays. We know this from our studies of basic optics. If I put a laser pointer through this door, it doesn't diffract. The reason it doesn't diffract is the length scale associated with this slit is huge compared to the wavelength. And under that condition, I can just think about ray optics. I don't have to think about diffraction or any wave-like property. The thing what we're learning here is that the geometric optics limit of quantum mechanics is classical mechanics. That is to say, so let me make this a little bit more apparent. Let's talk more about the geometric optics limit. Wave optics. So let's go back to the Helmholtz equation that we had before. Let's think about now. Let's talk about an electromagnetic wave moving in an inhomogeneous dielectric. So let's say I have a dielectric that's a function of position. And I want to know what is the wave equation that describes this. Yeah, I gotta scratch your head for a moment. You go through Max's equations, you get the following. Let's say this is a wave with frequency omega. So let's just talk about the time independent. That's the equation. Now, generally, you have to solve that with the boundary conditions. It's not an easy thing to solve, that problem. However, if the way in which this is changing over space is much, much, much slower than omega over k, then I have an approximate solution. Where there's a local wave vector, I would say, if this were a constant, we know what the wave vector is. The wave vector is omega over c times the index of refraction. And the index of refraction is the square root of the dielectric constant. Right? But now what I'm saying is that there's a local index of refraction at every position in this inhomogeneous dielectric. And it says there's a ray that moves through there with a local wave vector that depends on the gradient of the index. And as long as the wavelength is much, much, much smaller than the length scale over which the dielectric changes, then I don't have to think about solving the wave equation. I just have a trajectory of a ray. So the upshot of all of this is that wave optics is to single particle wave mechanics as ray optics is to classical mechanics. classical mechanics is the ray optics limit of the wave equation. Oh wait, there's still more. So let's look at this particular, oh, I should say, that, of course, if we didn't take this limit and we just looked at, this equation, including this circular term, which is sometimes known as the quantum potential, this is exact. We just took Schrödinger's equation, we separated out the real imaginary parts. And it's tempting, and people do follow this, that to say that really what's going on is that there's a particle that is moving in a combination of the physical potential and this quantum potential. And that's known as the de Broglie-Bohm guided pilot wave theory. As I say, the particle is guided through, and something having to do with the wave function. The wave function itself, the amplitude of the wave function, provides something that guides the particle in sort of an effective potential. It's very hard to generalize this theory to anything more than a single particle moving in a potential. So whether this really has anything to do with the reality of quantum mechanics or not, I think is highly questionable. But people work quite hard to try to think about, well, that's really what's going on. There's really both a particle and a wave. The wave just guides the particle. What do you do? All right. So let's look at the Hamilton-Jacobi equation in the case that I have for a stationary state. So now my wave function the time dependence I can factor out. Okay? And so this thing is a function of position, and then there's a phase that is typically called W. So that tells me that this Hamilton's principal function separates into a spatial part and a temporal part of this form. Okay, combining these two together. This is known as Hamilton's characteristic function. All right, let's plug that in to the Hamilton-Jacobi equation, which is the equation that comes from Schrödinger's equation when we've taken the limit of geometric optics. Okay? And what we get then is the following. The gradient of W squared plus the of x is equal to 8. That's to say that the gradient of W is the square root of the energy minus the potential energy times 2A. That is to say, this is the classical momentum at that position. Right? Because you subtract the potential energy, you got the kinetic energy, this is the momentum. So that tells me, integrating this, that W x is the integral of this over some path from some initial point to some final point, P classical x prime at dl. So that gives us this geometric optics limit, the same approximation to the wave function. In the short wavelength limit, the wave function, or the stationary state wave function, function of position, is some amplitude, which we still have to calculate, e to the I where the classical value of the momentum of the position is the square root of 2n e minus b. Thanks. Just like we wrote down over here. So this is approximate in this limit. It's a solution to the wave equation in that limit. What about the amplitude? What is the amplitude of the wave function? That is to say, the magnitude is what I really want to say. Well, we have the continuity equation. This is a stationary state, right? That's what I'm looking at here. What can you tell me about the probability density as a function of time? It's not changing. It's not a function of time. So the rho dt is 0. But the rho dt is minus the divergence of probability current, right? And what's the probability current? Well, the probability current is the local probability density times the gradient of the phase over momentum. That's what we said. But this is equal to whatever that classical momentum is at that position overhead. And this, well, obviously doesn't matter. Okay, let's look at this, for example, in one spatial dimension. So that we just have everything moves in 1D. Well, we have a solution to this equation. The solution says the local probability density at that position is some constant divided by this. Does that make sense in a kind of classical limit? This is saying that in this limit, the probability density to find the particle moving at this position is 1 over its velocity. Sure, if it's moving very slowly, it's very likely to be at that position. If it's moving very fast, then at any time interval, I'm very unlikely to find it there. So this is just what you would expect from just classical particle moving. And so putting that all together, we get an approximate form of the wave function. It says that the wave function, the stationary state wave function is approximately to some normalization constant, the square root of n over, it's the square root of that constant, whatever. This is called some normalization constant, classical at that x, e to the I. And this form, this approximate solution for the wave function in this limit of short wavelengths compared to the particle is known as the WKB approximation. And I forget I know this is Briwan, this is probably Kramer's, but I forget who W is. The WKB approximation is an extremely simple way to solve for the energy eigenstates. You've done it. You just know what the classical momentum is, and that's the geometric optics limit. All right, now I want to get just one piece deeper into here. And I want to talk more deeply about particles versus waves. Trajectories and wavefronts. And make this connection deeper between, in what sense is the classical dynamics like the quantum dynamics, in what sense it is different? Okay. To do that, I want to first quickly review in 2 minutes classical mechanics. Okay? So, let me do that in following. Okay. So, what do we know classically? So let's say we know a particle moves along a trajectory. Okay? So there's some trajectory as a function of time. There's some position at the initial time, and there's some function or position at some later time. And we know that this trajectory can be obtained as the stationary solution to the action. Right? So we have the action, which is a functional of the trajectory. Let's just say, so the action, I'm calling it S for depends on the particular trajectory. And given that trajectory, what I do is I integrate the Lagrangian, which I substitute in that trajectory, and it's time derivative for that particular trajectory, integrated over time from the initial final time. Okay? The Lagrangian for this simple case of a particle moving in a potential is the kinetic energy minus the potential energy. Right? And we know the solutions to Euler-Lagrange equations. Of course, we also know that we can write this in terms of Hamiltonian mechanics. We define the canonical momentum that way. And we define the Hamiltonian as a function of position and momentum. As the canonical momentum dotted into x dot minus the Lagrangian evaluated x dot as kilogram. So with that, we have another expression for the action expressed in terms of position and momentum trajectory rather than just a position. Solving this is that integral. Let's write it loosely like that. And let's put all that in. Right. Okay, so that's equal to the integral p dot x dot dt minus the integral of the Hamiltonian dt, or the integral p dot dx minus the integral h dt. Doesn't that look familiar? Suppose we were moving along a trajectory that had a constant energy. Then h is a constant. And this is just e times the time difference. This action, classical action, is exactly what we had over there. The phase factor that sits in our wave function is the action. However, we know that there's only one possible trajectory that takes us from here to here, the one that is the stationary action. That's the one that leads. Right? However, quantumly, there's no reason that I have just the one that has the stationary phase. In principle, all possible paths can take me from here to here. And I weight them by this probability amplitude. The one that was the classical solution is the one where slight perturbations around that don't change anything. So what it's saying is that when I'm in the geometric optics limit, the path that has the dominant contribution is the classical path. But when I'm not in the geometric optics limit, I have all possible paths. And that leads us to the notion of the path integral, which unfortunately we don't have time to discuss. Maybe we'll have a homework problem. I was going to try to do it, but we're out of time. And everyone wants to know about the path integral, because it's cool. But I'll just state what the result is. What's the result? So if I want to treat this problem quantum mechanically, what am I doing? I'm saying, I'm looking at the problem where, suppose at t0, I'm at a position. It's not I can never really do that, but I can analyze it mathematically. So I'm at a position, I'm in state. And I want to know the probability amplitude so that the state at a later time is that. How do I calculate that? What's the mathematical expression? I told you at that time t0, this is the wave function, and I want to know what is the wave, how would I calculate it? Exactly. Thank you. So, initially, this is my state. I evolve for a time that takes me from t0 to t1. And then I look at this. This is known as the propagator. It is the position matrix element of the time evolution operator. It's sometimes called K, or kernel, or corporal for somebody.
Corporal C.
Okay. And so this, you can plug it in. I'll have notes on this if we don't have homework for sure. What one can show is that this is equal to the following. This was part of Feynman's PhD thesis, the great Richard Feynman. What is this represent? This is every possible path that can connect me from those 2 points. I weight that with a phase factor that depends on the classical action. This is an integral over all paths. In the limit, that h bar is a tiny, tiny thing, generally, all these different paths are going to kind of cancel each other out.
Because they don't have the same phase, or?
They have wildly different phases. So I have waves that look like this, and then waves that look like that, and they all destructively interfere because if I slightly change the path, and an S changes slightly, but h bar is tiny, then that phase changes by a lot. And because the phase changes by a lot, it goes from this phase to all of a sudden that phase. And so on average, it washes out. It's only the ones that are near the case where the phase doesn't change a lot for a small change in the trajectory. That is to say, the case of the stationary solutions, which will contribute the most to this integral when this is big compared to h bar. But this is not just about the classical limit, this is about, in general, this is a way of writing the time evolution that connects the classical picture with the quantum picture. The connection is, classically, the trajectory is the one that gives us stationary action, and that's this path. But quantumly, all possible paths contribute to going from here to here, and they interfere with one another. When I have the geometric optics limit, there is a dominant ray, but in general, all contribute. Yes?
So I guess quantum mechanically, if like the paths themselves, they don't have to be close to the, I guess, the classical
Right.
path that have higher amplitudes or higher
Not
probability.
necessarily, yeah. So, for example, suppose I have a potential well, and I send in a particle. Classically, what's going to happen? Well, here, it has some energy. Now it's going to speed up, and then it's going to slow down. Quantum mechanically, it can reflect. Classically, that will never happen. That's a path very far. Now, of course, that's only going to be true if the wavelength of the particle is on the order of this well. If the wavelength is tiny compared to the size of this well, well then it'll just be like geometric optics. There'll be no reflection in that case. I want to make one last comment because although we described this in terms of pure states, and we talked about the classical limit coming from being at short wavelengths, it's not exactly the full story. What's important is the coherence length. The question of whether there is interference between. I can have a situation where the wavelength is small, but somehow I've allowed the coherence length to get big, and still see wave effects of something somewhat macroscopic. For example, there have been recent experiments that have seen diffraction of a virus. If you can cool down the position of the virus enough to keep its coherence big enough, even though it's a somewhat macroscopic thing, it can diffract and end up on the screen with a probability that depends on wave mechanics. So it's not just that it's macroscopic, it's about its coherence. All right, let us quit for today, and we'll talk about particle box.